So good afternoon, everyone. Good morning, good evening, wherever you're calling in from. And thanks for joining today's webinar that we are organizing. And it's on one of our tools we recently open sourced. And the tool is called PowerImpedanceACDC.jl. So it's an open source tool for performing small signal stability analysis of AC/DC systems, and it's complementing another tool that we released some time ago, which is called the Z tool. But Jan will talk more about how those two relate to each other later on. So before handing over the microphone to Jan, let me just quickly take a few minutes to say who we are. Myself, I'm Chef Beek, I'm a professor at KU Leuven, and also linked to Etch, which is the Energy Transmission Competence Hub we established within Energyville. And within this competence hub, we are pioneering research in the field of future-proofing our electricity networks, where we see a large-scale integration of HVDC technology and underground cables. So our activities are centered on research, on training, on setting up a brand new lab infrastructure, and on having an industrial ecosystem to do that together with our partners to ensure knowledge and technology transfer towards the industry. We're focusing on 4 key activities, 4 challenges to enable more undergrounding in the system, to ensure an adequate protection of such a future power system, to mitigate and deal with control interactions coming from the converters, and to set up resilient HVDC grids. So here you have the 4 different challenges outlined, slightly different words, and today we will talk mainly about the 3rd challenge, which is control interactions, and that's also the research that I'm conducting with the team. For that, we need tools. We need new types of tools that allow us to de-risk future installations of converters to make sure they don't interact with the power system, they don't interact with already existing equipment with other converters. And we can either do that by having a scan on models we don't know, which is a bit time consuming, but if we are able to build an analytical model that really allows us to speed up things significantly, and that's why we established the PowerImpedanceACDC tool. And with that, Jan, I think the time is right to hand over the floor to you, because otherwise I'll steal all of your thunder, maybe.
Okay, thanks, Jeff, for this introduction, and also from my side, a warm welcome. So welcome to the webinar on PowerImpedanceACDC.jl. So this is an open source tool for small signal stability analysis of AC/DC systems. And let's have a quick look on the menu for today. So there are a couple of things I will walk you through. So first of all, we will start off with an introduction. So basically looking at the power system dynamics, and looking at things that can go wrong in the power system. And then I will go over why frequency domain methods might be a very good idea to address stability challenges, to analyze stability in converter-dominated power systems. After that, we will quickly, not too much, dive into the frequency domain stability analysis. So how can we use frequency domain methods to get insights into the dynamics of power system to analyze the stability? Then we will go over the open source tool, PowerImpedanceACDC. So we will go over a couple of slides that explain the tool to you. Then there are a couple of examples to show the functionalities and capabilities of the tool. Last but not least, summary, conclusion, and of course, there will be the chance for you to ask questions. Okay, let's start. So we have seen increased oscillation in the power systems, and these oscillations started first in the 1990s in railway system through the proliferation of voltage source converters. And then this phenomenon has been spreading all the power system, PV system. We have been seeing this in wind farm systems. in HVDC systems, so on and so forth. And so those oscillations, they can be in different frequency ranges. So not only low frequency oscillation, they can also be at a very high frequency. So for example, here, this is a low frequency oscillation recorded in Australia, in a grid in Australia in 2020. The third picture depicts a high frequency oscillation in the kilohertz range in a grid in Europe. So we see that those oscillations are happening in a wide frequency range. And the origin for those oscillations depicted here, it's a small signal behavior of the system. Okay, so wide frequency domain. So wide frequency domain may be a very good method to study those phenomena. So first of all, with the frequency domain, we can cover a wide range of dynamic phenomena. So we can go from low frequency to very high frequency. And as you have seen earlier, it's important that we cover the whole spectrum to really cover oscillations in the whole frequency spectrum. Then you don't necessarily need mathematical models. This is what Jeff hinted upon. So we can just scan a device, basically a black box, in order to predict the vendor's IP, extract the frequency response, and do quite nice things with that. Then frequency domain methods are quite meaningful. So it's not only, you can not only derive device level insights, but also system level insights and also mitigation. Frequency domain itself is very modular and scalable. So you can aggregate buses in the system, which you will see in an example 2 I've prepared for today. And then small signal is the underlying cause of the oscillations. I mentioned that. And the system is operating the small signal regime most of the time. So it makes pretty much sense to evaluate the equilibrium of the system in order to assess the stability of the system. So, and this is something this can be nicely done in the frequency domain. Let's see. Go. Let's go a little bit back to the basics. So what is the transfer function? What is the frequency response? So think of a system as a box with inputs and outputs. So the input here is denoted as U, the output is denoted as Y. And the box is defined by a transfer behavior, which is basically a transfer function. And this transfer function is denoted as capital G, and it's a function of frequency. And this transfer function tells you how a certain sinusoid at the input is shifted in phase at the output, and also basically amplified at the output. So this is what I mentioned. So the transfer function gives you the ratio between the two, between the phase on the one hand and the magnitude on the one hand, and then you do this across the frequency range. So basically, at the input, you have sinusoids at different frequencies, and then you derive a transfer function, or more accurately, it's actually the frequency response of the transfer function. With this frequency response, we can do a lot of nice things. You maybe heard about Nyquist. So with Nyquist, we can assess whether a feedback loop will be stable or not. This is one thing we can do, but we can do much more. So we can calculate oscillatory modes in the system. We can calculate participation factors. We can also look at the passivity of the individual subsystems. So there are a lot of things we can actually do with those quite basic mathematical models, I would say. So a quick hint, the slide before, it was a zero system. So it was a transfer function. So we had one input on the one hand, and we had one output on the other hand. So one input and one output. And so we can generalize that. We can generalize this for an arbitrary number of inputs and an arbitrary number of outputs. So the inputs denoted here as M, and the outputs denoted here as N. And then you can get a transfer matrix, N times M, and which describes the input-output behavior of a multiple input, multiple output system. All right, so these were some basics about the frequency domain. And now we have a kind of grasp how everything works in frequency domain. And now let me now turn to how we can use frequency domain to characterize devices in the power system. So what you do, you're going to start by decoupling the power system at the generating buses. And then you're going to obtain the frequency response of those devices standalone. You can generalize that here to the nth order, to n devices. And then you can group the frequency response of those devices in a block diagonal matrix, which is here denoted as yn. So this is one part of the system, but the other part of the system is the existing network, so your passive devices. And we need two, because so far we just have the active elements grouped in one matrix. But in order for the system to interact, you need a transmission line in order to basically so that those devices can communicate with each other and also with the power system itself. So, therefore, for the existing network, we form our nodal admittance matrix. We use also for power flow calculations. Now it's frequency dependent. And with those two subsystems, when you do the math, you can derive a feedback loop, a negative feedback loop. So in the feedback loop, we have on top the transmission network, here represented by impedance. So the input is the current, the output is the voltage. And then we have our active devices represented as admittance in this block diagonal matrix. So with active devices, I mean converters, synchronous generators, all the devices that are not pure passives, basically. All right, and now when you see a feedback loop, you always want to know one thing: is it stable or not? So this meaning, is the power system stable or not? So in order to check that, we can apply Nyquist and more generalized Nyquist, because we have a MIMO system. And if we assume that the subsystems are individually stable, so we don't have right half plane poles in those different subsystems, then we can apply general Nyquist in the following way. We just check if the eigenvalue loci of this, of the product of z and product of y, does not encircle the -1 point. If it does not encircle the -1 point, the system is stable. If it encircles the -1 point, we know the system is not stable. All right, so this is already insightful, but now we just know whether the power system is stable or not. We cannot develop any mitigation methods. We just have a 0 or 1 kind of result from our stability analysis, and that's kind of boring. So we can do actually more. So when you derive the closed loop dynamics of a power system, which is here denoted as the closed loop bus impedance matrix, then you can see that the poles of the closed loop bus impedance matrix are the eigenvalues of your state space matrix A. So this means we can identify oscillatory modes by doing an eigenvalue decomposition of the closed loop bus impedance matrix. What we're doing here, we're employing a modal transformation. You've probably seen this earlier. You calculate your left eigenvectors of your matrix, you calculate your right eigenvectors of the matrix, you group them into a matrix, into matrices, and then when you multiply with your matrix, you get a diagonalized matrix. And this is the eigenvalue decomposition of our closed loop bus impedance matrix. And what does it tell us? It tells us something very nice, because when you look at the peaks of those eigenvalues, they tell you the oscillatory modes that are existent in the system. And so here's an example where you can see, so I have plotted here the eigenvalues across the frequency range, and there we can see dominant peaks. And those peaks we see, those are the oscillatory modes in the system. So when we push the system, we know the system is going to oscillate at those modes. We don't know whether those modes are stable or not, but this is something we did before with Nyquist. All right, so there's also one thing which is very insightful. I find we can also calculate the participation factors. So this is basically a sensitivity matrix which relates the modes to buses in the system. So then we can say where a certain mode will be present in which buses in the system. And if you want to read more about it, this paper is I find it written very well. You can read it here. All right, now I want to touch upon one thing which, is kind of a hot topic in literature and in academia in general. I think we can really say that that's passivity. And suppose we have two subsystems, and both subsystems are stable, and they are in a negative feedback loop. Then we can say that the closed loop will be passive and it will be also stable. So passivity implies stability of the closed loop, which is really nice. And the non-passivity we are not sure. So if one of the boxes, is non-passive, then we don't know whether the closed loop is stable or not. So why everyone gets super excited about passivity in the context of power systems? This is because this is a feedback loop I derived earlier. So it tells us about the stability in the power system. And the transmission network is passive because we have only passive elements in the system. And you can think of passivity as the property of a system to not generate energy. So a passive system can dissipate the energy that is inside or dissipate the energy that is introduced into the system, but it cannot generate energy by its own. So if we can guarantee that our sources or loads or converters basically are passive, then we know that this closed loop will be always stable. What means passivity in case of CISO? In case of CISO, it means that we have the real part of the transfer function is 0 or greater than 0. This means that the system is phase bounded. And this is very intuitive in case of CISO system. In case we have a multiple input, multiple output system, I lose any visualization here. Maybe you don't, but I do. Then basically just the maths needs to pan out. And so in order to check whether a MIMO system is passive or not, you calculate the Hermitian matrix and do the sum with the normal matrix and calculate the minimum eigenvalue. When the minimum eigenvalue is greater or equal to 0, then the system is passive. All right, with that, I would like to conclude the small summary of frequency domain methods applied to the power system. And now I would like to turn our attention a little bit more to the core of today's presentation. This is power impedance ACDC. So with power impedance ACDC, we can do a state-of-the-art frequency domain stability analysis of ACDC power systems. We have generic validated wideband models within the tool. Wideband models, because you have seen earlier, stability oscillation can be in a lower frequency range, but also in a higher frequency range. So with this tool, we want to capture everything, like the whole frequency range. This is what I just mentioned, capturing slow and fast dynamics of modern power systems. And since we are relying on analytical models, and this is also what Jeff already hinted upon, we are very fast. So we can do fast stability analysis of ACDC grids. So if you want to have a look at the repo, feel free to scan it. But yeah, you will see the QR code a couple of more times. So as you know, this tool is open source, basically because we are relying on nothing new. So all the tools, all the methods we have been implementing in this tool are state-of-the-art methods. We, with this open source path, we want to accelerate industry uptake for academic research and also enable collaboration with new approaches and solutions. Let me lose some words on Julia. So you might already have asked yourself, okay, why are these guys not going to Python? Because Python is like very common, I would say. You see it in many open source tools, also in the power system. This is simply because Julia is very performant. It can be very, very fast. And if you do it properly, it can reach C speed. So very, very fast, much faster than Python. So this is one reason, of course. The other reason is that we, within Julia, we have a vast ecosystem of scientific computing, and you have really nice packages. We are also using PowerImpedanceACDC. So this is very important to us. So this is also a reason why we are relying on Julia, not on a different language. All right, so let's have a look under the hood of the tool. So what is going on? What kind of models are do we have implemented in this tool? So there are two buckets of models, I like to call them, we have implemented in the tool. They are the passive devices and the active devices. The passives are natively modeled in the frequency domain, and we do this with ABCD parameters. So on the passive side, we have overhead lines, we have cables, we have transformers, we have impedances and I/O sources. On the active side of things, we have modular multi-level converter as the state-of-the-art HVDC converter. We have two-level converters, which you can also use as the AC/DC interface, but also for the representation of wind farms, for example. And then we have the synchronous generator. So here we are doing DQ domain state space model to model the dynamics of these guys. And in order to reconcile those two, we convert the state space into the frequency domain with input-output transfer matrices. Another important point is that all the models we have implemented are rigorously validated against their EMT counterparts. So we really wanted to be sure the models we put inside the package are really matching their EMT counterparts. All right, so another important aspect of PowerImpedanceACDC is that we employ throughout the package a two-port modeling of all the components within the package. You might have heard about two ports. That's not a problem. It's very easy to understand. So a two-port is a linear electrical network with two pairs of terminals. And there are different coordinates, I like to call them, in order to describe the two-port behavior. So two ports are frequency domain methods or frequency domain models of components. And so there are the set parameters, so impedance, so where your independent variable are your current injections at the ports, and you get your voltage out. Then you got the admittance parameters, where independent parameters are voltages, and then the currents are functions of the voltages and of course also of your Y parameters. And there are also the ABCD parameters, which is basically the native formulation when you do accurate transmission line model. All right. So each component is represented as a two-port in the tool. Okay, fair enough, I mentioned that. For the passives, two-port modeling is native. I mentioned that as well. For the active, again, we have to transform the state space into a transfer function representation. All right, so how do we do this two-port framework in the tool? For that, I have prepared a small example. So the power system here evidently is not a complete power system, but for the sake of showing how the tool works, it's just consists of three components. So if we go into the system in the tool, we connect the different ports of the elements. So in this case, we connect the AC side of the MMC to the AC side of the overhead line. And for the DC side of the MMC, we connect the DC side of the MMC to the DC side of the cable. Very important here is that ports can be multidimensional. In case of the MMC, at the AC port is multidimensional, or also what we say, it has two pins. So basically it has two ports, and the DC port has only one pin. All right, so let me now turn to the modeling we did for the different components. So there are several passive elements available in the tool. We have overhead lines, we have cables, we have transformers, we have impedances and I/O sources. In my opinion, this is probably all you need to model a model power system. And I already hinted on that. All of those components, all the passives, are natively modeled in the frequency domain. And we also did that to capture frequency dependency of component. And this is very important for power lines, because power lines, they are quite frequency dependent and higher frequencies. So the parameters change. So the resistance changes and the inductance of the power line also changes at higher frequencies. And if you want to have like accurate model of your overhead line, then you also need to capture the frequency dependency of your component. For the transmission line, we employ a frequency dependent line model with distributed parameters. This model is highly modifiable. So in case of the overhead line, you can do various tower realizations. The geometries of conductors, ground wires can be modified. You can change the number of subconductors in a bundle. So it's really a lot you can do. It basically matches the PSCAD modeling when it comes to overhead line. There are also DC and AC overhead lines organizations possible. So this is also very important. So we can also, with the tool, we can also model DC overhead lines. For the cables, we do a coaxial modeling of the cables. So the cables we are modeling are all coaxial cables so far. And we can go up to 4 conducting layers and 4 insulating layers for the cables, which means we can even model offshore cables, which usually have 3 conducting layers and 3 insulating layers, 1 additional layer for the armoring. And then you can group those cables into a cable group of, so you can group N cables into a cable group. So you can model a DC cable system, you can model an AC cable system. Another more recent feature is that we can also import transmission line constants from various tools, PSCAD here in this case. So when you have a very complex cable system, crossband cable, for example, or maybe a mixed system with type cables, coaxial cables, so very complicated. You can do the modeling in PSCAD, export your shunt impedance matrix and your series impedance matrix, and then you can still run your stability analysis in PowerImpedanceACDC. And of course, there's also the option to include frequency scans of a 2-part representation of transmission line. Okay, one more slide on the modeling of passives. So we also have a detailed transformer model. It's possible to do a 1-phase or 3-phase configuration. Different winding configurations are possible. And also we upgraded the normal 50 Hertz classical transformer model by having lump capacitors at the terminal to represent electrical couplings at higher frequencies. And additionally, we also integrated a frequency-dependent winding resistor. And with that, we have a very accurate transformer model, which also captures the dynamics of a transformer up to 10 kilohertz, roughly speaking. And this definitely exceeds the common EMT transformer models you have in EMT tools. Regarding the impedance, it's very modular. You can do a lot of things. So you can do arbitrary phase configurations. You can even define each element individually. So here you can see each element is defined by a different transfer function. So that is quite nice. And the sources are idle AC and DC sources. And in order to represent grid equivalence, you can, for example, combine either AC source with the impedance to get it Thevenin equivalent. All right, let me now turn to the modeling of the active elements. So I mentioned that we are doing a state space modeling of the active elements. These guys are non-linear, so we have a non-linear state space in the Q domain. So we need to linearize the state space in order to extract our frequency responses. And we have 3 components, a modular multi-level converter, modeling also the AC-DC side, a 2-level converter, AC-DC side, and synchronous generator. So I find with those 3 components, you can already do a lot of studies. And probably with that, we are capturing a lot of use cases in modern power systems. The MMC model is a multiple DQ frame model, so we're able to also capture the internal periodic trajectories you have in your MMC up to 150 Hertz. We have various grid forming implementations and also various grid following implementations for the MMC available. For the 2-level, so far it's only grid following available, and the synchronous generator is a model with an AVR. All right, so now I have been mentioning these models we have implemented to quite a lot. I also wanted to show you that these models are really matching, and I'm not telling you something which is not true. So again, all of the available components have been validated against the EMT counterpart. And for that, we use the Z tool to extract the frequency domain data from PSCAD. So if you're interested in this tool, you know the drill. You can scan the QR code and have a look at the Z tool. So here you can see the short circuit impedance of a three-phase overhead line and 90 kilometers in DQ. And you see first when you look, okay, it looks very good. So really the curves are on top. If you zoom in a little bit and if you look at the high frequency response of the overhead line, you see that we accurately capture the resonances, anti-resonances of the overhead power line. So again, we see here that our model, our analytical model matches the EMT counterpart from 0.01 hertz up to, yeah, I think I went up to 5 kilohertz. So this is really nice. So we really have a wide band match here. Another modulation, validation. I want to show here is the validation of a grid from MMC we did, and so also you can see here we have accurate match between the frequency response in EMT and power impedance ACDC. So you see the models we have implemented are wideband models, and they are matching across the wide frequency range. All right, so now I would like to give you guys a little bit of taste how the tool works. Let's have a look under the hood. So the tool revolves around a function, or it's actually a macro, it's not a function. That's the core of the tool. I see it like this. And so in this network macro, you first define your grid elements. So here, for example, is an element definition. So you guessed it, the constructor is MMC. So the element is an MMC. And you first define your basic parameters. You define your base power, you define your base voltages, turns ratio of transformer, etc., and so forth. And then also your electric circuit parameters, and then your control parameters. And with that, the model is defined. And you do this, of course, for all the elements you have in the network. You do this for overhead lines, you do this for generators, load, etc., etc. If you did this, then we can continue with connecting the elements via ports. So again, we are employing here two-port representation of each element. So we have to connect the ports, or called in the tool as pins, in order to construct our network. So you do this for your network components, and then your network is defined. Then the code checks whether we have active elements in the code or not. If we don't have active elements in the code, we can take a shortcut. If we have active elements in the code, we need to obtain the steady state solution for our nonlinear state space, and then we have to linearize our state space to get the frequency domain representation. So so we run first the power flow to get our angles and our voltages, and for that we are relying on the Julia package PowerImpedanceACDC.jl. If you're interested, you can scan the QR code here. So we code the internal interface to this tool to solve the power flow of our AC/DC grid. So for the AC grid, we are doing a positive sequence power flow. For the DC grid, it's a monopolar power flow representation. And yeah, then we have power flow representations for the different components, transmission line, transformers, impedances, converters. Converters are modeled by an AC/DC converter station, and synchronous generators are represented as a PV bus. So nothing fancy, all the things you know from basic course on power system modeling. All right, so with the operating point, we can get our solver running, solving for the steady state of the system. And when we form the steady state of the system, we can linearize and obtain our A, B, C, D matrix. And then we can obtain the frequency response representation of the actives, which are modeled as an admittance. Yeah. And that's a shortcut I have been talking of. When you don't have any active elements, then you can make things even faster. You don't have to solve a power flow, you don't have to solve for the steady state, and you can directly go to the end. So after completion of this network macro, so after completion of the core of the tool, all the components are defined as 2 ports in the frequency domain. However, we need to transfer them back and forth sometimes because the actives are formalized and the passives are formalized in ABCD. So we have several transformations in the tool, so we can transform from ABCD to Y back and forth, and also from phase domain to the Q domain. Okay, so I want to just give you a quick overview about like all the functionalities we have in the tool. So the most important functionality of the tool is for sure the automated stability assessment of ACDC systems via generalized Nyquist criterion. So this is what I mentioned earlier in the frequency domain methods. So I really want to stress here that this is automated. So you don't have to construct your matrices on your own. Of course, network on your own, for sure, right? But then the tool takes care of everything. So it constructs the corresponding matrices, and by calling the corresponding functions, you get the stability result. And what is really nice for GNC, for generalized Nyquist, you also got the terminal result. So you got the result in the terminal and see whether the system is stable or not. And you can also see the stability buffers, the margins, in case you run the stability assessment. Then the tool PowerImpedance can do a oscillation mode identification via eigenvalue decomposition. And we use the positive mode damping criterion in order to assess which kind of those modes you see, those peaks, are unstable. And then the tool can do a bus participation factor, so to pinpoint where we see oscillation mode in the system. Then the tool can also do impedance determination from an arbitrary bus into the system via modified nodal analysis. And then the tool can also determine the zeros and poles of the active elements via the linearized state space. And the code can also do a passivity analysis of your systems. All right, now I would like to turn to 2 examples to show the capabilities of the tool. So the first example is the multi-bus stability analysis. So the power system here, we have a wind farm, offshore wind farm connected to AC connection, and also we have HVDC links here to bring the power on shore. Using generalized Nyquist criterion in power impedance, we see that generalized Nyquist predicts that the system is unstable, simply because we see that the eigenloci, eigenvalue 15, encircles the critical point. So we know that the system is unstable. So this is predicted by power impedance. But we can do more. The tool actually can do more. So using the eigenvalue decomposition in the tool, we can have a look at the oscillatory modes in the system. And then using the tool again, we are employing the positive mode damping criterion. And this tells us that this peak, this oscillatory mode, is actually undamped. So it's an undamped mode at 55 Hertz. Using the participation factor function in the tool, we see that we have a concentration of 3 buses into this unstable mode. And these are the buses where you have generation. So you could think of this undamped mode as interaction between those generating buses in the system. All right, so this is what power impedance predicts. If we do an EMT simulation and build the system in a team tool and perturb the system, then we see we have undamped oscillation in generation buses. And we see that the undamped oscillation is 56 Hertz. We can really see that power impedance predicts accurately this instability in this system. All right, having an unstable system is something that it's not nice. So you can, with the tool, you could try various mitigation methods. Here, we're doing a wind farm PLL retuning. So we're changing the tuning of the wind farm. And when we change the tuning of the wind farm and use PowerImpedance again, then we see that we don't have any encirclement of the -1 point anymore. And this means that the system is stable. And this is also validated by MT. So when we perturb the system and we have retuned the wind farm, we see the system is stable. So again, we see PowerImpedance accurately predicting the stability here in this case. Example 2 is the integration case study. So this system has been built in PowerImpedance. And you can think that this is the regrid, right? So we just have one in-feed. You can think of those power lines, they're quite long. And then we have wind turbines here, grid following, behaving as a current source, not really conducive to system strength. So, so then there might be the idea to implement a grid forming StatCom to just control the voltage in a better way and to provide system strength to the system. So the question is here, when we place a grid forming StatCom at bus 9, is the system stable or not? Now we can do a single bus stability. Now this is one of the nice things you can do with this impedance-based stability framework, because we know the impedance seen from this bus looking to the system is a stable impedance, because the grid itself, as it stands without the StatCom, is a stable system. The StatCom, we did a proper StatCom design. The StatCom is also stable, standalone stable. So in this grid integration study, we'll first start off with obtaining the impedance. Example 2 integration case study. Yeah, I think, yeah. So I left off explaining how we do this grid integration study. So first we're going to obtain the impedance Z grid as seen from bus 9. So this is basically the impedance when we look into the system from bus 9. And here we can use the built-in feature within the tool. So there's a function called determine impedance. With that, we can determine the impedance seen from any bus of the system. Then we obtain the converter admittance. So modeling the converter and power impedance is very straightforward. So we can also do grid forming StatCom, that's not a problem. Then applying GNC to check whether the feedback connection is stable. And then you can add some sugar on top to loop through a couple of scenarios. For example, you might want to check the stability of the system when the topology in the grid changes, or when the operating point changes. All right, so if you just connect the StatCom and use the GNC function within the tool, we see that we have an encirclement of the -1 point. So this means if we were to close the loop, meaning connect the StatCom to the system, it would be unstable. And here, this is something I already mentioned before. The tool also gives an output and tells you whether the system is stable or not, and also tells you what are the stability margins. So you can change between gain margin, phase margin, and vector margin. So weak grid plus StatCom, not good, is unstable. And this is also proven here in MT. So what you see here is actually a well-known problem, and you see it in literature. So when you have a grid forming StatCom with, for example, with virtual, in this case with a virtual impedance, and you connect it to the weak grid, then you have to do some, you have to be careful how you tune your virtual impedance in order to keep the system stable. So one solution is the retuning of the virtual impedance loop. So this is what I'm going to show in a bit. But I just want to highlight that this is very quick within the tool. So you can do a fast recalculation of your admittance matrix of your grid forming converter. And this is really leveraging the speed of analytical models. So this is the bandwidth of a filter in the virtual impedance loop. And when you decrease the bandwidth of this filter, you see that the encirclement goes back. Basically, your eigenlocally retracts into the origin. And you don't have any encirclements anymore. And this is also shown in this figure. So on the x-axis, you see the bandwidth of the filter. On the y-axis, you see the minimum gain margin. And then you see when you reduce the bandwidth of the filter, you're going to obtain a stable system. So the base case was 1000 radians per second, clearly unstable, shown in EMT, shown in power impedance. And then with optimized grid forming control, with a cutoff frequency around 400 radians per second, you see that the system is stable. So again, power impedance accurately predicts the stability results you also see in EMT simulations. All right, so there's some future functionalities to come, so please stay tuned. But of course, if you want to reach out for something you might find valuable to have in the tool or have suggestions, stuff like that, please feel free to reach out, because that's the whole idea behind doing this open source. Last but not least, I want to just point out that this tool was not a single person effort, like not a one-man show, maybe more one army show. So there are plenty of people who have contributed over the past 4 to 5 years to this tool. And I think this should be definitely pointed out, because everybody contributed quite considerable to this tool. Of course, other open source tools within Etch. So I already hinted upon the Z tool, but there are also other tools, for example, DS analysis for more harmonic state space modeling. And you know the drill. If you want to have a look into those tools, you can scan the QR code. And that's already a wrap. So that's the end of my presentation today. So we have seen that small signal stability issues in converter-dominated power systems are something that exists and need to be solved and mitigated. And we have seen that frequency domain methods are a very powerful tool and mature and de-risk solutions. And we are proposing in this webinar PowerImpedanceACDC, which provides a stability analysis of AC/DC power systems. It relies on state-of-the-art frequency domain methods. It uses wideband models, which have been rigorously validated against EMT simulations, so we cannot even capture, we can capture low and high frequency aspects of stability. And of course, we opted for an open source approach, so feel free if you want to collaborate with us. And if you have any questions, please let me know and write something in the chat. Thank you.
Thank you, Jan. We already have a number of questions in the Q&A, if you can see it.
Maybe Beke can check it out and read it.
Yes, so the first question, how do you connect the two DC cables with the 1 MMC pin?
Yeah, that's a very good question, because I was a little bit quick on that. So the thing is, when you do a DC cable modeling, you actually got 2 pins, because you have 2 cables, right? So you have of each side of your cable, you have 2 ports. But this clashes with the MMC modeling, because the MMC, let me go just a little bit quick here. Because the MMC has only 1 pin at the side, so the MMC just takes a pole-to-pole DC voltage. So what you can do then, you can do a model transformation of your admittance, of your cable admittance, and then you keep the return mode and skip the ground mode, because you assume that your system, the DC system, is symmetric. And then you collapse basically your cable to 1 pin at each port.
Okay, thank you. Another question, why split a system like this in Y node and Z grid?
Okay, so let me go there. I think that's a very crucial question. So basically, you can split the system in arbitrary ways. But if you do that, then you might going to have right half pole planes in the loop gain. So again, the loop gain is defined like this. And that's not a problem. You can still have right half pole planes in the system. But you must know how many right half pole planes have. You must know about the multiplicity of those right half pole planes to apply generalized Nyquist in the correct way. Okay. When we split it like this, we can guarantee that we don't have any right half pole planes. in our subsystems. And then we can employ this, let's say this framework of just looking at the -1 point and check if you have encirclements or not. So what I just said is not 100% correct, because you can also have actually white half-pole planes in your admittance presentation of your MMC. For example, when you do DC control, I think it actually doesn't matter if you do it on the DC or AC side. In both cases, you get a right half-pole plane in the admittance representation of MMC at the origin. But in this case, you can deal with it if you just do indentation around this point on the imaginary axis. And then you can still employ this framework here, where you just look if the eigenloci encircles your critical point.
Okay, thank you. And then the last question, how do you convert between the different TQ frames of the devices?
Yeah, so so the thing is, when you have when you do the modeling of the active devices in your DQ DQ frame, the formulation or the admittance or the impedance you get from your device will depend on how you rotate your DQ frame, right? So this is because the those elements are not DQ symmetric in the lower frequency range. They are DQ symmetric in the higher frequencies, but they are DQ asymmetric. So it depends how you evaluate, in which frame you evaluate those DQ admittances. So we are doing this by basically transferring all those admittances into a global reference frame, and for that we choose the global reference frame is aligned aligned with the real axis. So basically we take the slack bus angle, which is 0. And then we express everything in this global reference frame, which makes it then possible to do stability analysis.
Okay, thank you. We had 2 additional questions coming in. For model validation, which PSCAD grid forming model did you use as a benchmark?
Yeah, this is a very good question. So we have our in-house models. So we don't use any generic models that are available on the internet. So we have in-house models, but for the validation, I used the averaged model to validate the here we go. To validate the analytical model power impedance against PSCAD, I used the average model of the grid forming asset. But I can also tell you I did this validation also with a switched model in PSCAD, and I also got a very good result. So I wouldn't say the match is a little bit different, but I'm bold to say that you can also get a very good match with a switched model.
Okay, thank you. And then the final question, would it be possible to use as a tool to build a system-wise Y-bus matrix for a given network, such as 39123 bus system?
Can you maybe repeat the question? I didn't really grasp it.
Yes, maybe you can check the screen, but would it be possible to use as a tool to build system-wise Y-bus matrix for a given network, such as 39/123 bus system?
Yeah, so is it...
So the question, Jan, is can you kind of use the package to build the bus, the Y-bus matrix essentially? And get
sure. I mean, that's what we are doing, right? So that's what we are doing to do the stability analysis to define the loop gain. Yeah, sure. And this is automated again. So yeah, it's possible.
Given that you have the proper parameters of the lines, well, you can also just put in lumped parameters and keep it simple. But if you want frequency dependent line parameters, you need to figure out what they might be for these systems.
Yeah. But the algorithm is implemented, and then it depends to you how you define your system. And but the algorithm just acts on what you give it to him, basically, what kind of models you give it to him. Yeah.
Okay, there are no further questions, so maybe we can close the session.
Yeah, so sorry, Bieke. Go ahead.
Thank you, Jan and Jeff. for all of the information, and thank you to all of the attendees.
So thanks for your interest in the tool, and as Jan pointed out, stay tuned for future upgrades and any feedback that you have. We would definitely like to receive it. So don't hesitate to reach out with your experiences and maybe a wish list. No guarantees there on any future implementations, but if what is on your wish list is also on our wish list, and when we see our need to include it, we might consider it. Thanks.
Thanks for listening.
See ya.
Bye-bye.